Hello everyone, we are thrilled to present our latest research in 3D computer vision here at CVPR, EscherNet, a generative model for scalable view synthesis. This project is a collaborative effort between the Dyson Robotics Lab at Imperial College and the University of Hong Kong. Drawing inspiration from the success of scalable training methods in language domains and 2D computer vision, we sought to extend this success to the domain of 3D computer vision. Our goal was to explore the development of scalable 3D foundation models capable of tasks such as 3D generation and novel view synthesis. There are several approaches to 3D generation using diffusion models. First, let's look at Dream Fusion. While Dream Fusion leverages pre-trained large-scale 2D priors to generate diverse and impressive objects, it faces significant limitations due to the lack of 3D priors. This results in expensive per-scene optimization and issues like the multi-face Janus problem. Next, 01 to 3 opened new possibilities by training a single-image to single-image diffusion model. However, 01 to 3 only considers a single view input and cannot handle multiple input views. More recently, multi-view diffusion models have been developed to generate more 3D consistent novel views. Despite this advancement, these methods are limited to generating views from a predefined set of poses and require full 3D data to render the desired posed views for training, which does not align with our design goals. Our work, EscherNet, addresses these challenges. First, it does not require per-scene optimization. Secondly, it generates more 3D consistent views. Thirdly, it can handle any number of input-output views. And finally, it generalizes to novel poses rather than being limited to a few fixed poses. Here, we present our method for encoding camera poses by formulating 3D vision purely as an image-to-image problem, similar to how transformers encode language as a sequence-to-sequence problem. In EscherNet, we encode 3D vision as a sequence-to-sequence problem as well. We consider each 3D scene as a set of 2D images, with the camera positions serving as the token positions. In the 4DOF object-centric case, we utilize a spherical coordinate system for representation. This includes 3 rotations and 1 translation along the view radius. In this system, all rotations and the translation are disentangled from each other. We designed our camera positional encoding to satisfy the following conditions, ensuring that it is only related to the relative positions of the cameras. In the 6DOF generic case, we have poses in the SE3 space, where each positional component is entangled. This complexity means we can no longer encode each component independently. Despite this, we still aim for our cape to capture only the relative pose transformation, maintaining its focus on the relative positions, as similar to rope designed in language models. In EscherNet, we leverage the original stable diffusion architecture with minimal modifications. Specifically, 1. Add our cape to the key and query in each attention layer to encode camera poses. 2. Replace the original language encoder with a lightweight image encoder. That's it! One of the remarkable aspects of transformers is their ability to generalize based on the number of tokens. In EscherNet, even though the model is trained on just 3 reference images to generate 3 target images, it can generalize to handle up to 100 reference images to generate 100 target images. This capability is truly impressive and allows us to achieve our goal of any-to-any generative novel view synthesis. Now let's look at our results compared to 01 to 3 and cross-check with our designed goals. As we can see, with more views provided, the novel views generated by EscherNet are more constrained and accurate. Our novel views demonstrate greater 3D consistency compared to those generated by other models. Additionally, we don't require per-scene optimization. Instead, we achieve our results with just 1 forward inference of the diffusion models, using 50 steps. EscherNet has been extensively tested on various datasets. For real-world images, our experiments yielded quite reasonable 360-degree novel view synthesis results, using 5 images captured from a camera. We also explored using off-the-shelf text-to-image models to generate images from user prompts. This approach was successful for both single-image input with Stable Diffusion XL and for 4-image input with MV Dream. Another application of EscherNet is in 3D reconstruction. By inputting EscherNet-generated views into 3D reconstruction methods such as news, we can obtain detailed mesh representations. Comparing EscherNet to other state-of-the-art diffusion models, our approach generates more 3D consistent novel views. As a result, we achieve more complete and higher quality reconstruction meshes. That's all, and for further questions, please find us at CVPR.